This video will pick up where we left off in class for Chapter 7. So if you remember, we went through constructing the distribution of sample means, so all of the possible sample means of a specific sample size from a population. And we talked a lot about the central limit theorem and how that tells us about the sampling distribution. Now, the first example that I'm going to cover, we actually covered in class, but I wanted to give it to you again, just in case you wanted to see it again. So basically what we're going to be doing for the rest of this video is using z-scores for the sample mean to determine where that sample mean would fall in the distribution of sample means. And it's really important to learn about this because this allows you to find the probability of any given sample. And you really would sometimes like to know how likely it is that your sample comes from, or in other words, how well it represents a population. So in experimental research, if we administer a treatment to the experimental group, then we expect a very low probability of randomly selecting a sample that matches the characteristics of our experimental group. And that's because the population at large hasn't been exposed to this experimentally manipulated treatment that our sample has been exposed to. So if our sample has an extreme mean after we manipulate something, some independent variable that we've manipulated that we think is going to have an impact on whatever we're measuring, or the dependent variable, then again, if that happens, we would expect to see an extreme mean, and also that it would be highly unlikely that we would be able to get this sample mean from the original population who hasn't had anything manipulated in it. Now, using the probability and the distribution of sample means is also really useful in just plain old observational research, even if you're not manipulating any conditions. So we can test our assumptions or test claims of others. So how likely is it that this outcome would happen in the population? You can see if the reported mean based on the population is suspect or suspicious, because if you find a sample that's supposed to come from this population and it's highly unlikely that it did, chances are the population parameters aren't accurate, assuming that you have a decent sampling strategy. Also, the z-scores, probability, and the sampling distribution can also be used to answer questions about the probability of events in the population, even when you don't have access to the raw data in the population. So we'll do a few examples to show you all the different ways that you can use the z-scores from the sampling distribution and the sampling or the unit normal table to find probabilities. So this first example, a simple random sample with replacement. So first we're going to talk about using z-scores when you are assuming that the samples are coming with replacement, being drawn with replacement. After we do some of these examples, I'll show you a distribution of sample means when we don't assume replacement, and then how you would calculate probabilities and z-scores for that. So let's start with replacement. So a simple random sample with replacement of 16 employees is selected from a normally distributed population, and in the population the mean is 50 and the standard deviation is 12 on a job knowledge exam. And this ranges from 0, the scores on the job knowledge exam range from 0 to 75, with 75 being the highest score possible, the most amount of knowledge on that exam. Now, real quick, I stress that this is a normal population because according to central limit theorem, we can't assume that the population, or we can't assume that the sampling distribution is normal when we have less than 30 people in our sample. But we know that even if there's less than 30 people in our sample, as long as the population distribution is normal, we don't have to worry about not being able to use the unit normal table to find probabilities. So let's get back to it. We've got these population parameters. We have a sample of 16 employees. We give them on-the-job training, and then we find that their mean on the job knowledge exam is 55. Now we can say, okay, well, their mean is larger than the mean in the population, so we can just say, oh, on-the-job training works. Well, that's not the case, because remember, because of sampling error, we're going to expect a difference anyway, even if on-the-job training did nothing at all. We're still going to expect some difference in job knowledge because we have a sample. We don't have everybody from the population, so there's going to be some error there. So the question is really, is this sample mean extreme based on how big our sample size is and how much error we would expect to see just due to chance, or in other words, the standard error? So to do these calculations, the first thing that you need to do is you need to calculate your z-score. So that's this formula here. And then looking at this formula, we know what the sample mean is, it's 55. We know what the population mean is, it's 50. Mu is 50. But we do not know what the standard error is. So that needs to be calculated first. So first thing you'll really do is calculate your standard error, which is the population standard deviation divided by the square root of the sample size. So according to this problem, the population standard deviation is 12, and the sample size is 16. So 12 divided by the square root of 16 becomes 12 divided by 4, and you end up with a standard error of 3. So this means that just due to chance, even if on-the-job training had no effect on job knowledge, we would expect to see a 3-point difference in job knowledge between a sample of 16 employees and the population at large, specifically this population. So moving on, now we want to compare the observed difference, the actual difference between the sample and the population on job knowledge, to the difference we would expect to see just due to chance, so the standard error. So the observed difference is 55 minus 50, which gives you 5. Compare that to the difference we would expect to see just due to chance, or the standard error, which is 3, and you end up with 1.67. So we could say that that's almost extreme. So 5 divided by 3. Oh, let's be better here. Thought that I did that. We went around to the thousands place, so 1.667. So the reason that I say this is almost extreme is because the loose criteria for an extreme z-score, which would tell you that your mean is extreme compared, or your sample mean is extreme compared to the population, you want to see a z-score around 2 or more to be considered extreme. This is almost 2, so we're thinking it may be extreme. To really hone in on that, is this extreme question though, you want to see the probability. So how likely is it to obtain a simple random sample with replacement with this level of job knowledge or higher if on-the-job training did not work? So this distribution represents all of the possible sample means of n equals 16 from this original population. But we're hoping that our sample no longer represents this original population so that it'll fall on the extreme end of this distribution. So if we draw out our sampling distribution, you'll see that the z-score for the population mean is 50. And remember, according to the central limit theorem, the population mean equals the mean of the sampling distribution. So we can plot that right in the middle here. So 50 is the mean of the sampling distribution. That always has a z-score of 0. And then if we plot out our z negative 1 and z positive 1, we just take this mean, subtract 1 standard error. So in other words, subtract 3 points. That gives us 47. And to find the z-score of positive 1, we just add 3 points, add 1 standard error. That gives us 53. And then the score that we were interested in finding was for an x value of 55. We found that z-score to be 1.67. Really 1.667. And so we can plot that here. And this is really useful because in order to find the probability that you would have a sample with this level of job knowledge or higher, you need to know if you're going to look for a tail or a body when you go to look in the unit normal table. So we found the z-score, it's 1.667, and we know that we're looking for the proportion in the tail, so we're looking for job knowledge of this level or higher, so higher scores will go this way. This is the smaller portion of the graph, so we are looking for a tail. So now what I need to do is I need to find my z-score of 1.667, which will be 1.67 in the table because it only goes to the hundreds place, and then locate the probability or the proportion in the tail associated with that z-score. So let's go ahead and look in this table. All right, 1.67 z-score. Scroll down. Oh, found it. And the proportion in the tail for a z-score of 1.67 is 0.0475. So 0.0475 is our answer. And you can write this out either way. You can say the probability of getting a mean, sample mean greater than 55, or the probability of getting a z-score for the mean greater than 167, those two things mean the same thing because the z-score for 55 is 1.67. So there you go. And I just kind of put a little note there that you are looking in the tail. And then 0.0475 is the probability associated with a score greater than 55. And this is highly unlikely. It's less than a 5% chance. So we're thinking that on-the-job training probably worked because this sample is highly unlikely this sample still comes from the original population who did not receive on-the-job training. So now let's do an example with an observational research. So that last example was about experimental research, which we don't really cover statistical significance or anything experimental in this class, but it is a good demonstration of how you can use the distribution of sample means and the unit normal table to find probabilities. So this next one is when we're going to test our assumptions or our claims about a product. So Titleist is trying to convince professional golfers to switch to their brand of drivers. They claim that a golf ball hit with their drivers travels a mean of 295 yards, so that's our population mean, with a standard deviation of 15. So that's our population standard deviation. And this is out of a population size of 600 professional golfers. So let's say that we're trying to test this claim that on average you'll hit the ball 295 yards with their driver. So let's say we have a simple random sample with replacement of 36 professional golfers, and we calculate their average drive to be 285 yards. Does this support this claim here? So at first glance, you might be led to believe that because 285, our sample mean, is less than 295, the claim of the population mean by Titleist, that this claim is not supported. But remember, the mean of 285 is based on a sample. And we know from the concept of sampling error that we never expect the sample mean to equal the population mean. The sample mean will be higher or lower depending on chance, not always due to actual differences, in this case, caused by the brand of the driver. So maybe we just randomly sampled professional golfers with less power in their drives. So the sample mean could be slightly lower than 295 and still support the claim, but we need to see if this sample mean is substantially lower than what we'd expect to see just due to chance, or in other words, based on the standard error. So let's go ahead and see that. And you see all the calculations here, but I'll walk you through it. So the first thing we need to do is to figure out how much difference will we expect to see between this sample and this population just due to chance. So we calculate our standard error using this formula, the standard deviation divided by the square root of n. Well, the standard deviation is given to you. It's 15. Sample size is 36. Plug those values in and do the math. You end up with 2.5 for your standard error. So on average, we would expect to see a 2.5 yard difference between a sample of 36 golfers and the population who has a mean of 295 and a standard deviation of 15 yards. So we can plug this value into the denominator of our z statistic, and the numerator is just the sample mean, which is 285 right here, minus 295, the population mean right here. So we divide our observed difference by the difference we would expect to see by chance, and we end up with -4. So one way that you can interpret this z-score is that the sample mean is 4 times lower because it's negative, 4 times lower than what we would expect to see just due to chance. So again, this sample mean difference is 4 times lower than the mean difference that we would expect to see just due to random chance. So we would call this an extreme z-score. So at this point, we're pretty suspicious that Titleist's claim is not accurate. But let me show you how to plot this out and then find the probability of associated with this sample. All right. So again, the middle of our distribution represents the population mean, which was 295, mean of 295. And then the sampling error, the standard error, was 2.5. So if you want to plot -1 and +1 z-scores, you take the mean minus 1 standard error. So 295 minus 2.5 gives you this. And then 295 plus 1 standard error of 2.5 gives you this 297. And I do that because it helps you draw your distribution, because your points of inflection should be right about at -1 and +1 z-scores. And it also helps to determine where your actual value that you're interested in will go and how extreme it is. So let's go ahead and say, all right, here's the score we're interested in, 285. And if we're asked how likely would it be to have a simple random sample with replacement with 36 people in it from this population with an average drive less than or equal to 285. Less than or equal to 285, that would be a tail. Now, real quick, we know that 285 is to the extreme left end of the distribution. We know it's to the left end because 285 is less than the mean, so it's to the left of the mean. And it's pretty extreme based on the fact that the z-score for it is a -4. So that's why I put it so far out here. So again, if we're looking for less than or equal to 285, it goes this way and it's a tail. So what you do is you go to the unit normal table, you find a z-score of 4. Oh, let's find it. And we look for the proportion in the tail, and we get 0.00003. So if you go back and look, 0.00003, very highly unlikely. So in other words, it's almost impossible that we would get a sample mean from 36 golfers that would be 285 yards or less if this claim was true. So we aren't buying it. We think that Titleist's claim is suspect. So now I want you guys to look at the handout for Chapter 7 and try the job satisfaction example that's on there. So I would encourage you to pause this video, try the job satisfaction example, and then restart it once you've already worked through it so that you can check your answers. Okay, so I'm hoping that you tried that example, and now I will show you what your answers should look like. All right, so job satisfaction is normally distributed with a mean of 4 and a standard deviation of 1 in the population of American employees. And I gave you the ratings here just so that this 4 is meaningful. So it's, right in the middle of being completely very dissatisfied and very satisfied. And then you're asked, which of the following outcomes is more likely to occur if I randomly sample workers in the U.S.? So you have two different scenarios. One is with an n equals 2, and we're looking for job satisfaction in the mean that's less or greater than 5. So that would 5 is just somewhat satisfied in this scale. Just want to put that in there for your information. And then in scenario B, we're looking for the same exact thing. We're looking for the probability of randomly selecting somebody from a sample with job satisfaction greater than somewhat satisfied, or 5 in the scale. But now our sample size is a bit larger. So this is just to show you how the results of your probability will change based on how large your sample size is. So before even doing this, you should be suspecting that, okay, well, I remember that sampling error decreases as my sample size increases. So we would expect to see that sort of change when we're looking at our data here. So let's see how this plays out. So the first thing you'd want to do, because really the end result is we want to get a z-score to then find probabilities. But before you can do your z-score, you need to calculate the standard error. So the standard error in scenario A, so it's still the standard deviation divided by the sample size. Well, in this one, the standard deviation for the population is 1, and that doesn't change based on the sample size. What does change is this denominator here. So in the first one, we're dividing by the square root of 2 because n is 2. Second one, we're dividing by the square root of 30 because in scenario B, n is 30. So when you do the math for that, you'll see that what you probably predicted actually happened. In scenario A, with the smaller sample, we have a larger amount of error. And then in scenario B, with the larger sample, we have a smaller amount of expected error between the sample mean and the population mean just due to chance. So then in step 2, you want to convert your sample means to z-scores using the sample mean, the population mean, and the standard error that you just calculated. So in both of these cases, I went ahead and recorded the important information that you'll need to do this. So here we've got our 2 standard errors. And up here you'll see that we're still looking at a sample mean of 5 across both compared to a population mean of 4. So we've got 5 minus 4 in both cases. The only thing that changes from scenario A to scenario B is the different standard errors that are plugged in the denominator. And you do the calculations for that, and you'll see that we have a smaller z-score here and a larger z-score here. So the reason that we have a smaller z-score in scenario A is because we have less people in our sample and more error. And if you have more error, then you're going to have a bigger number here in the denominator, and the overall value of z will be smaller. So the next one, this one had the larger sample, smaller error, larger z. So if you think about the relationship between z-scores and probabilities, if you have more extreme z-scores, then you have smaller probabilities of getting that result. So just looking at this before we look at probability, this is a larger z-score. So that means that this is a far less likely outcome. And that's because we don't expect such extremes, 5 compared to 4. We don't really expect that many differences with a larger sample because we think it's going to be more representative of the population. Whereas with a smaller sample, we aren't really expecting that to be highly unlikely to be different from the population because smaller samples tend to be very different from the population anyway. So if you plotted in step 3 your sampling distributions and you plotted them accurately, you would see that this first distribution is a little bit fatter, so the points of inflection come a little bit farther apart because we have, if you look here, more standard error. So more spread in our means. And if you plot your -1 z-score and +1 z-score, you would see that for a +1, it would be 4.707 would be the mean corresponding with a z-score of 1, which in other words is just 4 plus 0.707 plus 1 standard deviation. Here, for the z -1, subtract 1 standard deviation, so 4 minus 0.707, and you would get 3.293, which is right about here. And just as always, the sample mean of 4 corresponds to a z-score of 0. And I use the same process over here, just with the different error. Now the most important thing is to see where your sample mean lies on this distribution, to then determine if we're looking for a tail or if we're looking for a body. So if we're looking for the probabilities of getting a sample mean greater than 5, and 5's here, greater than goes this way, and we're looking at tails in both situations. So the next step, step 4, is to find these probabilities in the tail based on the z-scores. So in part A, our z-score was 1.41, 4, but in the table it's 1.41. And then in part B, our z-score was 5.464, 5.46 in the table. So if you go to the table and you look for 1.41, keep on going, 1.41, the proportion in the tail is 0.0793. So that's pretty unlikely. So if we go back, you'll see that 0.0793. Now if you look in the table, you'll see that it only goes to 4. So literally 5.46 is off the charts. So we could just pretty much say it's pretty much impossible. There is some sort of probability associated with it. That table is not all inclusive, but it's extremely low, and it's lower than the probability of getting an extreme sample mean, or in this case a sample mean of 5, when you have a smaller sample. So remember, this goes with the larger sample, this goes with the smaller sample, and it's more likely to get a sample mean different from your population mean with a small sample than it is with a large sample. And that's what this conclusion here represents. And I'll put all of this on Canvas for you guys too, so you'll have these notes to look at and study. Okay, so now let's look at the sampling distribution when we aren't assuming replacement. So we have a simple random sample without replacement. So first thing I want to point out is that on the handout there was actually a math error. I put 6 here instead of 2, and I'll talk about this in more detail in a second, but I just want to point that out, that there is an error in your handout but this will be posted on Canvas, and I want you to refer to this so that you don't get confused. So make sure that that is the sample size, so 2, and not how many samples you have. Okay, anyway, so when we don't assume replacement, then we don't have repeats. So if you remember before, where we were able to have one sample that was, 1 and 1, and another sample that was 2 and 2, you won't have that when it's without replacement. So this is the same population that we used for the first example that we did in class, only now it's without replacement. So you can compare the two if you'd like to see the difference. And so, again, you can't have a sample with the same person twice if we're assuming that these scores represent scores for 4 different people, because it's without replacement. So, for instance, whenever we sample this person, we can't sample them again within the same sample. They're out of the running. They're out of the population. So we can't have repeats. And also, when you sample without replacement, you're not going to have a repeat of the same combination of scores. So if you see here where we've got 1 and 2, you will not see a 2 and 1 anywhere here like you would if we weren't sampling without replacement, if we were actually replacing. So just wanted to point that out. That's a difference between the two. And these are highlighted because what you do is you take every single possible combination of 2, n equals 2, in this example, of this population. So 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. And then you calculate the means for all those possible samples. Something else I want to point out too, see how we see sample 2, sample 3, sample 4, sample 7, sample 8, and sample 12? That's also to help you compare these different possible samples to the one that we did at the beginning of class when we were sampling with replacement. All right, back to the matter at hand. So these are all of our possible 2-number combinations from this population, and we're saying 2-number combinations because our sample size is 2. And then you find the mean for all of these. So 1 plus 2 divided by 2 is 1.5. 1 plus 3 divided by 2 is 2, and so on and so forth. And we're dividing by 2 because there's 2 scores here. So remember the mean, you add the scores together, divide by how many scores that you have. So if we add all these means together, we get 15, which is the sum of all the means. And we can plug that into this formula to make sure that the mean that we calculate equals the population mean. So luckily, the central limit theorem with regards to the mean holds up even when we sample without replacement. So in other words, the mean for our sampling distribution without replacement still equals the mean for the population mean, just like the mean for the sampling distribution with replacement equals the population mean. So another good way to check your work is to make sure that the mean of this sampling distribution, so adding all these scores together, dividing by the total number of samples, so 15 divided by 6, is equal to the population mean. Now these scores are highlighted because these represent the contents of the sampling distribution, and these are what we'll use eventually to put them into a frequency distribution table to see what the sampling distribution would look like if we drew it by hand. Now the next thing, whenever you don't have replacement, you're sampling without replacement, you have to make a correction to the standard error formula. So instead of just having this for the standard error, you have to take the standard error and multiply it by this here, which is the square root of the population size minus the sample size divided by the population size minus 1. And these are all the calculations for how to do that. So an easy way to do it is to start off with just calculating plain old standard error, what you would do if we had replacement. So that's the population standard deviation divided by the square root of the sample size. Here's our population standard deviation that we calculated in class. And the sample size is 2. So 1.118 divided by the square root of 2 becomes 1.118 divided by 1.4142. You do that math, and this would be the standard error if we were sampling with replacement. But we aren't, so we have to take this into account as well to correct for that. So we can plug this 0.791 that we already found into this formula right here, and then replace big N, uppercase N, with the population size, replace lowercase n with the sample size, then replace uppercase N with the population size, and then subtract by 1. So if we simplify this, we'll keep this 0.791, 4 minus 2 is 2, 4 minus 1 is 3. Then if you, next step, take the square, or take 2 divided by 3, you get 0.6667. So that's just the next step. Then you take the square root of that, you get 0.8165. And then we multiply these two together. So the original standard error, if we were sampling with replacement, multiplied by this correction factor, and the standard error that we would calculate would be 0.646. Now remember, before we were looking at taking the population size to the power of the sample size to figure out how many samples we should have. Well, that doesn't hold when we're sampling without replacement. You can use the counting rule for combinations to figure out how many samples you should have in the sampling distribution. And this is from chapter 5. We didn't talk about it, but here it is. And this is the formula you would use. So you would use the population size, the factorial of that, divided by the factorial of the sample size, multiplied by the factorial of the population minus the sample size. And that seems complicated, but it's really not. Factorial just means that you multiply every number between that number and 1, all the whole numbers, to get the factorial version of that number. So for instance, our population size is 4, so 4 factorial is 4 times 3 times 2 times 1. If we were looking for 6 factorial, it would be 6 times 5 times 4 times 3 times 2 times 1. And you can actually get this value if you just use the calculator on your computer. There's a little factorial thing if you go to View Scientific. So if we do 4, see this, factorial, you can get 24. Or you could say, well, I know what factorial is. It's every whole number between the number I'm interested in, 1, so 4 times 2, let's do 4 times 3, just to be logical, times 2 times 1, and you get the same answer. Just wanted to show you that in the calculator on your computer. All right, so we already figured out 4 factorial is 24. And then 2 factorial is just 2 times 1, so 2 times 1 is 2. And then here, 4 minus 2 is 2. So we've got our 2 factorial here. But guess what? 2 factorial is just 2 times 1. So if we take 2 times 1, we get 4 right here. So that's where that comes from. 24 divided by 4 is 6. And lo and behold, we have 6 unique samples of a sample size of 2 from this population. So that's another way to check your work. So not only do you want to make sure that the mean of your sampling distribution equals the mean for the population, but you also want to make sure that you have the correct number of samples based on this formula here. All right, so plotting the sampling distribution. So if we look at just these numbers, all these possible sample means of this specific sample size from this population, and create a frequency distribution table with that, then we have what it takes to plot them out in a frequency distribution graph. So we have a range of 1.5 being the lowest to 3.5 being the highest, so all the values in between, and then you count how many of those you have here. So we have 1, 1.5, there we go. We have 1, 2 right here. We have 2 2.5s right here, 1, 3, and then 1, 3.5, and that's reflected here. You don't have to find these probabilities, but I'm just showing you that when you have the actual raw data, when you have every single possible sample mean of a specific sample size from this population, you could hand calculate the probabilities, but when we don't have this information, we use the unit normal table to find these probabilities. And that's most often the case. We don't usually have this information because we usually work with much larger samples and much larger populations. Okay. So if we wanted to turn this into a frequency distribution graph, this is what it would look like. So we've got our range of mean values starting with the lowest to the highest, and then we would draw bars up to the frequencies associated with those means. And look, it's a normal distribution. So central limit theorem also holds up for this when it comes to shape. And if you have a very, very skewed population distribution, it will normalize around the same sample size as it would with replacement, so around 30 or more people or objects in your sample. Okay, another thing I want to point out is that this distribution is a little bit skinnier if we drew, a little shape around it. It's less variability than when you sample with replacement. So remember, the standard error with replacement was 0.791, and now if we take 0.791 times this correction factor, it decreases the standard error a little bit. All right, so here's another example. So this is an example where you can use the sampling distribution to answer questions about the probability of certain events in some group that you're interested in, even when you don't have access to all the raw data in the population. So this example, on average, American coal miners, and I actually looked this data up, there's 88,000 of them, and they live to be about 53 years old on average with a standard deviation of 5. So how likely is it that all coal miners working at Prosperity Mine in Indiana, where there's 353 employees, and we're assuming no replacement, right? We're not going to want to include every single employee more than once. So how likely is it that all these employees, based on these population parameters, will live to be older than 67 and begin receiving Social Security retirement benefits? So the first thing that you want to do, so remember, we're going from an X value, which is 67, to a probability value. So we need to find the z-score for that. So the first step is to find this denominator here. We already know what the numerator of X, or what z is. That's our sample mean minus our population mean. That's right here. But we don't know what the denominator is. So the first step I would do is just find the standard error without the correction. So plug in the standard deviation of 5 here, divided by the sample size of 353, the square root of that. So the square root of 353 becomes 18.7883. So then you're left with 5 divided by 18.7883, and you get 0.266. So now we have part of this formula here, this part. So let's find this next. So the square root of the population size minus the sample size divided by the population size minus 1. So we plug in our population and our samples here in the correct spots. We do the calculations, and we end up with 0.998 as the correction factor here. So now we want to go ahead and find the z-score. So in the denominator, so the numerator doesn't change. We already had that information to start. And then the denominator, I say, okay, 0.266 times the correction factor that we just found. And then we end up with 1467 minus 53 divided by this times this times this, 0.2655. 14 divided by 0.2655 is 52.731. This is a huge, 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 huge z-score. I can tell you right now, it's going to be off the charts if we try to find it. There is no z equals 52 on those charts. It's very extreme, and it's pretty much impossible that you would have every single employee in this mine live to be retirement age or older. So if we plotted this out on the sampling distribution, the population mean is 53. It's right there in the middle with a z-score of 0. And then if we wanted to, kind of see where most of our means would be expected to fall within one standard error of the mean, so z -1 to z +1. If we take 53 and subtract this corrected standard error, this 0.2655, you'll get 52.675. You take 53 and add that corrected standard error, you get 53.266, or 0.2655. I rounded to the thousandths place. And so looking at that, where would this z-score of 52 fall? Well, it's off the charts. It's probably pretty much impossible that it is a possible sample mean that we would get from this population. That's why it doesn't even really fall on this graph. And so that's the crazy high z-score for this age of 67 that we use to calculate the z-score. Okay. So now I want you to try the example that's on your handout, where we are now doing the same thing that we did before when we were trying to test the claim from Titleist. Only now we are doing it assuming that the sample was without replacement. So pause this video, try it out for yourself on the handout, and then come back to see if your answers were correct. Okay, so now let's look at the answers. So same example as before, our sample size is still 36, and we're trying to see how likely it would be to have an average drive from the sample that's less than or equal to the sample mean of 285, if in fact the average is 295 in the population with a standard deviation of 15. So first thing we want to do is find this standard error with the correction factor, so we'll have the denominator of z. So you plug in the standard deviation for the population, which is 15, divide that by the sample size, which is 36, and then you plug that into your formula, and you end up with 2.5. So remember, that was the standard error that we found when we did this before, when we were assuming replacement. Remember, that's not our standard error anymore, because we have to do this correction. So now we take 2.5 and we're going to multiply that by this correction. So you plug in your population size, your sample size, and then your population size here. Solve for that, and you get 0.970. Now we have everything we need for the denominator of z, and we already had everything we needed for the numerator. We've got our sample mean here and our population mean here. So our sample mean minus our population mean, so 285 minus 295, divided by the standard error times this correction factor, this 0.970. We end up with negative 10 divided by 2.425, and we get negative 4.124. So this is very extreme in this case. We would say this is an extreme sample. Not very likely to see that. So now if you go down here and you look at the plots, and again, it's good to plot things so you can know if you're looking at a tail or a body. The population mean is in the middle, has a z-score of 0, and then a z-score of -1 is the population mean minus this expected standard error. And then a z-score of 1 is the population mean, 295, plus this expected standard error. And if we plot this out, this 285, we know that it's going to be pretty far out in this distribution because the z-score is so large. Even though it's negative, it's still a large z-score just on the left of the mean. So we plot these out, and we know that if we're looking for less than or equal to 285, we're going out this way, and this is definitely a tail. And if you see, there is nothing higher than 4 on the chart. So we could say that it's off the charts. The probability is off the charts. It's pretty much impossible that this claim is accurate, which is kind of the same conclusion that we had before. Only now the math is a little bit different because we're not assuming replacement. So this negative 4.124, when we did this same exact problem when we were assuming replacement, the z-score was -4. So it's not that much different. And the reason that that happens is because the population size is pretty large, 600, relative to the sample size. So whenever the population size is large compared to the sample size, in fact, when the population size is more than 20 times the sample size, which is the case here, then that finite correction factor that we've been using, you can pretty much ignore it and just use the simpler formula because the difference is not that severe. There's not that much of a difference. So just to kind of summarize everything that was talked about in Chapter 7. So when you're working with samples, you're always going to expect a difference between the sample mean and the population mean. So there's always going to be some sampling error. And the size of this sampling error, so the difference between a sample and a population mean, depends on the size of the sample. So if you have a larger sample, you're going to expect less error. It also depends on the variability of scores in the population. So if you have more spread in your scores in the population, then you're going to expect more error. So bigger sample size, less error, more variability in the population, you're going to expect more error. And the standard error that we've been calculating, this little guy right here, or this one if you're doing sampling without replacement, that is the expected difference between any given sample mean of a specific sample size and the population. So it's just a measure of sampling error that's used in the Z formula for the mean. So the standard error is a specific measure of sampling error, and it tells you the expected difference between any given sample mean of a specific sample size and the population. And the sampling distribution, so what's represented here and what we actually found by hand here, that just tells you all possible random samples of a specific sample size, so in this case 2, from this population. And according to the central limit theorem, the sampling distribution will be normal when you have a sample size that's 30 or more, or when the population distribution is not normal. But remember, even if the population distribution is not normal, the sampling distribution will be when you do have that sample size greater than or equal to 30. And that's really important because this unit normal table that we've been using, well, heck, normal's in the title of the table, and it relies on a normal distribution to be accurate. Also, the mean for the sampling distribution will equal the mean of the population, in both cases with or without replacement. And then the standard error can be calculated with either this formula with replacement or this formula without replacement. And the standard error is basically just the standard deviation of the sampling distribution. So I hope that this video was useful for you and prepares you to finish or start your computational and your conceptual knowledge checks for Chapter 7. And again, we talked about a lot of this stuff in class. This is just what we did not have time to cover because we spent a lot of time talking about the quiz and brainstorming for some neat ideas of how to make this class a little bit better and to help you guys learn the material and walk away from this class knowing the material well. So make sure that you check the syllabus that I posted today, which is the 21st of November, to see all the changes that were made to the schedule. All right. Happy Thanksgiving.